Good morning. Today, I'd like to finish up talking about the basic integration rules, including some situations where we actually use that completing the square business. I'd like to do an example integral that uses at least one, maybe more, of these five formulas labeled 11 through 15. To begin with, I'm going to look at the integral of tangent x plus secant x. By itself, this isn't on the list of formulas that we know, but if you think of it this way, I'm doing the integral of a sum of two things. If I know how to do the integrals separately, then I'll do that, add the results together, and put the constant of integration in. Thinking that way, I do know an antiderivative for tangent x. It's on the list. I also know one for secant x. So this problem is very easy. Keeping those facts in mind, I can just write the answer down. Notice that if I felt like it, I could use properties of logarithms to further simplify this. I have the logarithm of something minus the logarithm of something else. I could write that as the logarithm of a fraction. And since 1 over cosine is secant, if I wanted to, I could write my final answer in this form. For mercenary purposes, any one of these three is a perfectly acceptable answer. There's an old joke that says when all you've got is a hammer, pretty soon everything starts looking like a nail to you. I've got the square of something plus 8 times the something. If I think that I've been recently talking about completing the square, and therefore everything should be about completing the square, I would take the 8, cut it in half to get 4, square that to get 16, add and subtract, and then try to take advantage of the fact that I have a perfect square now. That is not what you want to do here. I can write my problem as the sum of two separate integrals. In the second one, I can pull the constant factor 8 out in front of the integral, and after doing this, this is on the list of things we know how to integrate, and so is that. Antiderivative for secant squared is tangent. An antiderivative for secant is natural log absolute secant plus tangent, so we can just write the answer down. By way of contrast, this is definitely not on my list of things that I know how to do, at least not in any obvious way. In this case, I am going to try completing the square on the bottom of the fraction. I do have a problem, though. The coefficient of the x squared bit is 4, not 1, which will complicate things just a little bit. I'm going to deal with the bottom of the fraction separately, then I'll put it back into the integral. There is a philosophical issue about how to deal with the 17. I could write 4x squared plus 4x in parentheses, do my completing the square, and then afterwards deal with the 17. Or I could just deal with it up front, which is what I'm going to do. I'm going to write 4x squared plus 4x plus 17 as 4 multiplied by x squared plus x plus 17 divided by 4. The coefficient of the x bit is 1. This is 1 times x. If you divide that by 2, you'll get a half, and I wish I had 1/2 squared added in. So I'll do that and correct for it. Then I have to deal with algebra. I've got my 4 outside the brackets. The first 3 terms amount to x plus 1/2 squared. I have 17 over 4 minus 1 over 4, which is 16 over 4, which is 4. which is 2 squared, I'm going to have 4 times the number 2 squared plus the square of x plus 1/2. Taking advantage of the algebra that we just did, the integral that I'm interested in is the same as that integral. I can bring a factor of 1/4 out front, and what's left is 1 over a constant squared plus some reasonably simple thing squared dx. We have a formula for this kind of situation. Formula number 19 on our big list of formulas says that the integral of 1 over a squared plus u squared du is 1 over a arctan u over a plus a constant. Looking at what we have, obviously a is going to be 2, and u is going to be x plus 1/2. Although it's not going to cause any difficulties in this case, we do need to philosophically be aware of the dx, so we'll be very explicit about this. Du dx is 1, so du and dx are the same. That's why it causes no issue. Letting a equal 2 and u equal x plus 1/2, this turns into this integral to do, which, using formula number 19, is straightforward as the 1/4 that I had outside the integral times 1 over a 1/2 arctan u over a. Altogether, this is 1/8 arctan x plus 1/2 over 2 plus a constant. If you thought it made it look better, you could write the x plus 1/2 divided by 2 as 2x plus 1 over 4, but that's purely cosmetic. This completes our review of basic integration techniques and completing the square. Hopefully, this has been easy enough to follow and also will sufficiently refamiliarize you with the kind of integration techniques we learned back in Calculus 1. Coming up soon, the first of our new integration methods, integration by parts, and a guide about how you should format things when you hand them in. Until then, I hope everybody has a good day. I'll talk to you again soon.